Thank you everyone for joining us for our webinar series, Power Hour. Today we're going to be discussing DOAS and high percentage outdoor air. With me, I've got our Seattle sales engineer, Scott Boucher.
Hello.
And we're missing a few other guys, but I'm in Spokane, the sales engineer over here for our Spokane office. Today we'll be discussing DOAS, high percentage outdoor air handlers, air source heat pumps, the new refrigerant change, a couple housekeeping duties. I'm going to mute. I got everyone muted right now. So we got clear audio. If you have a question, just enter it in the chat and we'll answer it. I think we're just going to answer it on the spot today, just to try to get some conversation going if that works. And then, yeah, our presenter is Bill Atkinson. He's a application engineer with Greenheck on the DOAS team. Super knowledgeable. Bill, thank you for joining us. I will hand it over to you.
Thanks, Blake. Thanks for having me and inviting Greenheck to this. So, yeah, again, my name is Bill Atkinson. I'm a applications engineer specifically for the DOAS group at Greenheck. And yeah, as you have questions, enter them in the chat, and I'd love to answer them right away and get a discussion going. A lot of times that's how we get a really nice presentation, is by getting your good questions out there and getting them answered. I'm going to cover a few things today. I'm going to cover just kind of the basics of DOAS, or dedicated outdoor air equipment, a few Greenheck specific things, but then I'll talk about A2L refrigerants and air source heat pumps and some of the improvements we've made with that. But let's dive into it. So I know a lot of you know this already, but dedicated outdoor air equipment, like it says, for bringing in large amounts of outside air, dehumidifying it, and putting it into spaces. Our most common application for that is education. Almost half the units that we make go on to schools, universities, things like that. Those spaces that have a lot of people in them, those people need outside air fresh into the space. Other applications, hotels, multifamily, healthcare, hospitals, exam rooms, things like that. Other places, they can be used in food service as well. So for kitchens and dining areas, or any other space that's got high occupancy or just large outside air requirements. Some specs on our range, a few different cabinet sizes. It's going to span 500 to 18,000 CFM in different cabinets. Cooling options, 3 to 70 tons of cooling. Energy recovery, you can get a unit with or without energy recovery, and I'll touch on that in a second here too. You get one option for heat and one option for cooling. It's mix and match, so you can select one option for cooling and a different one for heating. Don't think you have to pair things up in specific ways. So for heating options, we can do an air source heat pump. So use that refrigeration unit for both heating and cooling. We can do electric heat, hot water coil, or indirect gas furnace. Options for cooling, again, that air source heat pump, a package DX, or chill water coil. So if you want to mix and match, you could do something like a chill water coil and electric heat, or you could do something like package DX and an indirect gas furnace and make a unit that way. Options for energy recovery. We have a RVE model, which is going to be a energy recovery wheel, either polymer or aluminum material on the wheel, or an RVC model, which is going to use a core and a polymer or fiber material for the core. Outlining our wheel units, so that RVE, and our core units, so the RVC. If you ask me, hey, what should I do? And even before you told me what your application was, if you're going to use energy recovery, my recommendation would be the polymer wheel. It has the highest effectiveness. It has the widest airflow ranges, so it really covers most of the bases that way. There are people out there that are interested in energy recovery cores. A a lot of the appeal is that there's no moving parts with that energy recovery core. So people that are worried about breakdowns or maintenance, a lot of times are attracted to that energy recovery core. And of course, it is true there are no moving components with the core. Economizer options. You do have a couple options for your energy recovery wheels. We can do a stop jog wheel. So that's where the energy recovery wheel just stops spinning during economizer mode. Modulating wheels where we'd slow the wheel down. It extends the economizer range a little bit, or we can do a bypass as well. Washing of wheels and cores. Polymer wheels can be slid out and they can be washed with mild detergent and water. Aluminum wheels can be vacuumed off. Fiber cores can be vacuumed as well. And then polymer cores can be washed with mild detergent and water. Washing every 3 to 5 years. So this isn't a super intensive washing that has to happen very frequently. So if you are checking on your filters and giving a look at your energy recovery device every once in a while, you should be okay with your maintenance on your energy recovery device. I want to take a second to mention our side return and our side discharge housings. So this is a standard offering. It's selectable. We can do side discharge and side return in each of our housings. So you don't have to do a plenum curb or other things like that if you're wanting to pad mount a DOAS unit out there. Obviously, trying to get away from something like this where a service platform had to be added and an extra curb. So in a case like this, you could just pad mount this and put the ducting straight into the building and avoid a lot of that extra cost there. Touch on construction for a second. On the left is one of our competitors. They have foam that they cut out and then they paste into their panels. They call that a panel. On the right is one of our panels at the factories. So it's metal on the outside and the inside. We then take spray foam and spray it on the inside. That foam expands into all the nooks and crannies and corners and crevices of the panel. Makes it really stiff. You can see some squeeze out here of the foam from where they put the foam in and also from the corners. Makes a really stiff panel. It's also insulated from sound and from thermally as well. I won't dwell on this too much. Pre-coat paint on the top, Greenheck. On the bottom, again, one of our competitors. So this is a permatector coating. All the material comes into the factory with coating on both sides of the material. Afterwards, it's cut, bent, and then assembled. So every single piece before it goes onto the unit has coating on it. There's no overlapped pieces that didn't get any coating or anything like that on it. And then obviously after a salt spray test, it still looks pretty good. This is showing the unit as a whole. Again, this is an RVE unit I'm showing here. A few things I want to point out for our units with refrigeration, so PDX or air source heat pump. You're always going to have a low sound condenser fan. So if you look closely here on the edge of the blade, there's some serrated edges that makes the fan quieter when it's operating. The lead condenser fan is always going to be variable speed. That's going to help us with our modular hot gas reheat. It's going to provide more reheat by being able to turn that fan down when more reheat's needed. For larger units, the lead compressor is always going to be variable speed. That'll be important as we talk about air source heat pump here in the next couple slides. So variable speed compressor, not a digital one that's going to load and unload. The units are at part load most of the time, right? Because we're not at our design day conditions most of the time. So that variable speed compressor is going to be more efficient at part load. And since we're at part load most of the time, that's pretty important. IG furnaces get a stainless steel heat exchanger. Fans are all direct drive plenum fans with VFDs. That's both for supply and exhaust. You do get a stainless steel drain pan underneath your DX or cold water coil. I talked about energy recovery already. You like to take a second to just show how the air moves through the cabinet here. I find a lot of people find it helpful. So I'll start on the right. Hopefully you can see my cursor. This is the OA hood. So this is where outside air would come in. So outside air is coming in. There's a filter before going through the energy recovery wheel. Our outside air damper is on top. Next would be the cooling section. So DX or chill water, air source heat pump, that would be here. Hot gas reheat coil would be next. Supply fan is on top here. So that's what's drawing the air through the cabinet here. After that, the air is going to come down and either come out the side or down through the bottom here. The heating section is in the bottom here. So I'm showing a indirect gas fired furnace here. But if you had something like electric heat, that would be down here too. On the return or exhaust side, return air would either come in the side or in the bottom here. For recirc units, this is the recirc damper, so air would come in here, and this is the mixing section. Exhaust air would go through the filter here before going through the wheel. And then you can see the exhaust blower down here in the bottom right. And the outlet for that exhaust air is on the back side of the unit there. So it's not directly underneath the outside air intake. New refrigerant. So obviously the EPA passed the technology transition rule, limiting refrigerant global warming potential to below 700 for residential and light commercial. So that does include us. Previously, so last year we were using refrigerant R410A, which was pretty common throughout the industry. Obviously, that is above that 700 limit for GWP, so we had to switch to something else. We switched to 454B, like a lot of our other manufacturers in this space. So it has a lower global warming potential of 675, so below that 700 threshold. Or excuse me, 466. R32 is 675. You hear this term A2L thrown out a lot. So the A2L is the safety group of this refrigerant. So there are different safety groups. 410A was a A1. So that was down here. So A1 means that it was not toxic and it did not have strong flame propagation. So all the A refrigerants are going to be low toxicity. All the B refrigerants are going to have toxicity. And then the number associated with it is going to indicate the flammability. So originally there was just A1, A2, A3, B1, B2, and B3. With 454B, they decided it is a little bit flammable, but it's not quite as flammable as the rest of the refrigerants in the A2 designation. So they came up with A2L, which is somewhat flammable, but not as flammable as the rest of A2. So they basically came up with a new classification, and that's kind of why there's this dashed line in here with the A2L and the star in here, showing that they have lower flammability than the rest of the A2s. So something that would be toxic might be something like ammonia. So obviously we're not using ammonia, but maybe in a large chiller or large process, you could have something like that. So that's an example of something that would be toxic. With the flammability, with the A2L rating of 454B, we do have to do a few extra things. So I will talk about that here on the next slide. So we do have to have leak detection. We do have that in the units. It comes standard if you have a refrigeration unit in your selection. So you don't need to worry about selecting anything or calling it out. It will definitely be in there no matter what. There's a few spots where the leak detection will be. So one will be by the compressor. That's the photo that I'm showing here. You can see the compressor on the right there, a leak detection sensor behind it. It will also be by the coil, so by the DX coil. And it'll also be in the supply cabinet as well. and by the furnace if you have a furnace. The idea is if a leak is detected, the sensor will change state, and then the unit will go into a leak mitigation sequence. What that'll do is it will shut off the compressor. It'll run the supply fan at a minimum speed. It'll close the OA damper and open the return. And then if you do have a leak in the IG furnace area, it'll shut off the IG furnace as well. All of our wiring diagrams have been updated to show these leak detection sensors. So if you do get a submittal or you're in caps, you can see it there. So these relays here are really the leak detection sensors. So there is dry contact inside of that sensor that you saw the picture of. So they will change state when they detect a leak. So that's these 1, 2, 3 here. And then these are the contacts for those sensors. The other thing I want to point out is what we're calling an A2L mitigation jumper. So that's this wire from 78 to 79. If somebody needs to test the leak detection system, they're able to come in, pull out that wire. The unit will then go into its mitigation sequence. We can confirm that that's working and then put that wire back in. Same thing for this one on the bottom here. Another requirement is that the fire alarm for the building be attached to the unit. So that's this wire 70 and this S6 contact we're showing. The idea with this requirement is that if there was a fire in the building, the unit is also leaking refrigerant at the same time, the leak mitigation sequence would then not run. The idea being we don't want to put slightly flammable refrigerant into a space that's already on fire and start fueling that fire. So that is here as well for you. Releasable refrigerant. So like I mentioned a couple slides ago, the refrigerant isn't toxic, so it can be diluted into the space. The idea with the mitigation sequence is that that refrigerant is not toxic. It is slightly flammable. The way to make it not flammable is to dilute it. The way to dilute it is to mix it with more air, put it into basically the spaces that are being served. Now, the problem would be is if you had a lot of refrigerant in a really small space, you wouldn't be able to dilute it enough. So there's a requirement that we tell you how much refrigerant is in that unit, and then how much airflow it needs, and then how big the spaces it has to serve. So all that is on the submittal. So if you do print out a submittal, you can find it there. I went ahead and selected our largest unit, which is going to be a 70-ton PDX unit. That unit has 61 pounds of charge in it. The minimum airflow is 1,653 CFM, which if you know this unit well, this unit would typically be flowing somewhere between 10 and 18,000 CFM typically. So this amount of air is pretty small. And again, with 70 tons, only serving 915 square feet would be almost a ridiculously small room for this type of unit to serve. So these requirements are pretty easy to meet unless you're doing something that's pretty not normal, put it that way. I'll touch on air source heat pump operation. I'm just going to cover the basics here. I'm not going to go into the nitty gritty of it, but the idea being there's the coil inside and there's the coil outside. Cooling mode, which we're usually most familiar with, the indoor coil is cold and the outdoor coil is hot. We're cooling the space inside. The reversing valve I'm showing here is the portion that changes when we need to switch between cooling mode and heating mode. And again, I'm not going to get into the details here, but just for any of the kids in the back of the classroom here. So for heating mode, that reversing valve is going to switch positions. The inside coil is going to get hot and the outdoor coil is going to be cold. Usually when we're heating, it's already cold outside, but the temperature of this outside coil will actually be below the ambient temperature outside. So if it's 40 degrees outside, the air source heat pump is in heating mode. This coil would be significantly colder than the outside temperature. So it might be something like 20 degrees out there. Some updates to our air source heat pump. So our offering for air source heat pump is going to be 5 to 30 tons of cooling and heating with that air source heat pump. We have a new low lockout temperature. So it used to be 10 degrees for 410A. Now with 454B, it's going to be down to 0. Will be our new low lockout temp. So the unit should operate as long as the outdoor temp is above 0. There's a few other requirements with that. We can get into that if there are questions around that. But if it's -1 out or lower, the air source heat pump will stop running. Now you always get a choice of supplemental heat with your air source heat pump. So with that air source heat pump, again, you could have electric resistance heating, you could have a hot water coil, you could have an indirect gas furnace so that you do have backup heat. Our efficiencies went up a little bit with 454B, so we're up to roughly 4.5 ISCOP with our units. That does change based on configurations and things like that, but that's kind of a general rule of thumb right now. I mentioned already that lead inverter compressor, and again, that's going to be critical here in a couple more bullet points. We also have that lead EC condenser fan. All of our air source heat pumps are going to be single circuit designs. So you may have multiple compressors, but they're all going to be in one circuit inside the unit. We added a few control sequences with 454B here. So we have a new cold start sequence. So this would be, suppose you did go below that 0 degree lockout temperature, the air source heat pump stops running for a while. There's a process or a procedure inside the controller to start that unit back up so it's able to start up cold. I got a question. Yeah.
Quick
What's the
question.
minimum air inlet temperature at the coil for the heat pump unit asking for units without energy recovery? Yeah, great question. So let's get into that. So on a unit without energy recovery, if the outside temperature is less than 10, the air entering the coil here has to be above 35. So if you're without energy recovery and you're 100% outside air, you would need to be above 10 outside for the air source heat pump to keep running. With energy recovery, you're pretty much always going to be above that 35. But in the case of a non-energy recovery, 100% outside air unit, you'd have to be above 10 outside. So that's, if you are doing that, use 10 as your kind of lockout temperature and you'll be okay. If you are able to keep that inlet temp to the DX coil above 35, you can run all the way down to 0. Is a standard leak dissection sequence able to specify edited? I'd imagine there'd be some where the engineer might prefer an open rather than a closed, let's say damper, for example. No, it's not able to be edited. But it is slightly different between units with and without recirculation dampers. So if you didn't have a recirculation damper, obviously it can't open or close. So in a 100% outdoor air unit without a damper, you're just going to put outside air into the space. But great question. Thank you, Scott and Mark. I mentioned the cold start sequence, boost speed. I'll talk about this in more detail on a following slide, but the idea is we're using that lead inverter compressor for when it is below 20 degrees outside, we can actually run the compressor faster. So typical rated speed would be about 6,000 RPS. We can run it up to 7,200 RPS. What it does, it gives us an increase in capacity, and I'll show that in a following slide here. Smart defrost. So I got a slide for that as well. I'll talk about that. I mentioned the supplemental or backup heat. So you are able to select your secondary heat as supplemental or backup. The difference being supplemental means that the air source heat pump, and if you have electric heat, that can run as well, so in tandem or together. Backup is the inverse of that. So if selected as backup, only the refrigeration unit will run or the electric heat will run, but never at the same time. And really the benefit of backup, if you can call it a benefit, is that you'll have a lower MCA and MOP because we're not sizing those to run both at the same time. The thing to really remember when you select backup is you don't have your backup heat available during defrost. So that is the big drawback of that. So if the unit does go into defrost, you don't have your backup heat. You don't have your secondary heat available if you have backup selected. So do keep that in mind. If you're hot water or indirect gas, you don't have to worry about that. It's always supplemental. That's basically just for electric heat units. Oh, I have that outlined here. Great. Backup, just like I said, either air source heat pumps running or electric heat, but never both. Lower MCAs and MOPs. Supplemental air source heat pump will do all of the heating if it's sized appropriately, and it can. If the air source heat pump couldn't keep up with the LAT request, the electric heat can fill in any gaps that are remaining there. So bring up the temperature to the LAT. And then obviously if the air source heat pump locks out, the electric heat does all the heating, but the MCAs and MOPs are higher because we size for both of them running at the same time. Designing with air source heat pump. So a few notes if you're trying to get a Greenheck DOAS unit with an air source heat pump, 500 to 12,500 CFM would be your range. 5 to 30 tons of cooling. One note with that, don't expect to get 12,500 CFM of cooling at 30 tons. You probably will run out, but if you are a partial recirc unit, you could probably get up to that 12,500. Recirculation air or energy recovery is really helpful with the air source heat pumps. Again, that comes back to that rule I was talking about where the DX coil needs to see above 35 if the outside air temperature is less than 10. But maybe you have design conditions there in Washington that are more favorable than 10, and you can get away with that. Do think about increasing your tonnage selection to increase your air source heat pump capacity. Especially if you were trying to design a unit that didn't have secondary heat. By going to a higher tonnage, you might end up with a cooling leaving air temperature, LAT, that's really low. It might be like 41 degrees, which is maybe too low. But what it might get you in return is that your heating capacity is higher. And so you can make a selection that works for the job that you're working on. Compressor boost speed, again, I'll talk about that in a second here. So let's talk about boost speed. So on this graph on the right, there's a few lines on here, but I have the ambient temperature. So this is the outside temperature on the bottom here. And then I have this relative load percentage here. But if we look at this blue line, if we ran the compressor at the rated speed, and we started on the top right here, and then we keep cooling the temperature outside, or the temperature outside goes down. The laws of thermodynamics tell us that our capacity is always going to start decreasing as the outside temperature goes down. I mentioned that compressor can run faster once we get to 20 degrees ambient outside. And so with that increase in speed of the compressor, we do gain capacity. So that's this boost speed here. So we gained some capacity when it got colder out, and we're able to have a little bit more capacity. So I'm not familiar with all the design conditions in Washington there, but if you did design a unit and you were designing around 22 as an outside condition for winter, you would not see boost speed. But if you did select something at 19, you would get it. So just be careful as you go about that. So if you were designing something at like 21 or 22 and it wasn't working for you, maybe putting in 19 would get you that boost speed, and you can see that you would have more capacity by doing that. The green dashed line here is a kind of fictitious building, but as it gets colder out, the building needs more heat. In this triangle here, I'm showing that if we didn't have boost speed, you would need aux heat during this period, and it kind of pushes the requirement for aux heat to the left here to a lower outside air temperature. Some of the questions I get around boost speed are my MCA and MOPs higher because of boost speed? And the answer is no. Right, this rated load here is really a proxy for how much power the compressor is consuming, right? So if we look to the right here, this 47-degree temperature, it's able to consume more power over here than during the boost speed period. So this doesn't increase our MCA or MOP. The other question is the compressor rated to run like that, or are you guys just hijacking it and running it faster? And the answer is no. This is a kind of a sanctioned operating condition from the compressor manufacturer. So they let us know that we can do this, and we took advantage of it. Last question I get is, will it wear out the compressor faster? And again, no. This is something the compressor manufacturer tells us that we're able to do, and it's not outside of their envelope. So smart defrost. As the outdoor temperature goes down, the outdoor coil gets colder. There is some moisture in that outside air. Can cause it to condense on that outside coil and freeze since it's below freezing temperature on the coil. So when that happens, the coil has to be defrosted because eventually it becomes so blocked up with ice that it becomes ineffective. So during the defrost cycle, the reversing valve is going to change position. The unit's going to go into cooling mode. The outdoor fans are going to turn off. The indoor fan will stay on. The outside coil will get hot. The inside coil will get cold. Since the outdoor coil is getting hot, the ice will start to fall off and melt and shed. What we're doing for our smart defrost is that we are only initiating the defrost sequence when it's really needed. So we are able to tell from the pressure sensor on the refrigeration circuit the temperature of the outside coil. And we know the outside temperature as well. So once that outside coil starts getting much, much colder than the outside air temperature, we know it's frosted. So at that point, we'll initiate the defrost cycle and shed that ice off. So we're not going to do it willy-nilly when it's not needed. All that time that's spent defrosting is not time that's spent heating the space. It's extra energy. So we don't want to do it if we don't have to. So that's why we've gone to this smart defrost. Now, the other advantage is we know when the coil gets hot too, when it's running in the defrost cycle. So once the outdoor coil gets hot enough, we know all the ice fell off, all the frost is gone, and we can go back to heating mode. So those two benefits of only doing it when we have to and only doing it for as long as we have to is what we're calling smart defrost, so that you can spend more time heating with that air source heat pump. Obviously saves energy for your customer, and works pretty well. I've yet to hear if any other manufacturers out there are doing this. I know there's a few requirements in Washington for energy recovery. I did look up before the meeting here. I think 60% ERR, or a sensible ratio of 68. Some things to consider as you're going through that. Like I mentioned in the beginning, that RVE model is going to give you higher ERRs, just because the wheel is more effective at transferring energy, especially that polymer wheel. It does help to balance outside air and exhaust air volumes exactly. If you can keep those balanced, the ERR tends to go up. If you are trying to do something or get an increased energy recovery ratio, jumping to the next housing size up usually helps. The the size of the energy recovery wheel is obviously limited by the cabinet. So if you go to a larger cabinet, you can get a larger energy recovery wheel, or you can get more cores inside of a unit, and that sometimes is enough to increase your ERR. Another option to consider is not having a bypass damper. So by not having a bypass damper, those would typically sit above and below an energy recovery wheel, or they would take up a spot where an energy recovery core would go. So by doing that, your area for energy recovery shrinks a little bit. That area is then not used for energy recovery, and your ERR tends to go down a little bit. So by not having a bypass damper, you get more energy recovery device, you get more energy recovery, your ERR tends to go up. So something I like to point out. Questions I get with that are, hey, if I don't have a bypass, I don't have economizer mode. That's not necessarily true. You can still do economizer mode through a wheel by stopping the wheel, like I mentioned in the beginning. Tougher on a core, you do need a bypass on a core, but for wheels, you can do economizer without a bypass damper. Some more tips for designing with air source heat pump. Again, most successful using that RVE model. Um, Utilize the highest effectiveness energy recovery you can. Do consider those lower LETs for cooling mode to get a higher capacity for heating mode. Partial recirc models will perform a little bit better in defrost than 100% OA units if you can do that. I take any more questions that you all have on a DOAS product, air source heat pumps, refrigerants, A2Ls, or any other burning questions that you got. I just can't do any of I don't know, marriage related questions or things like that, but anything HVAC I'll try to answer.
Yeah, I have. This is Scott with Dorsey. I have one. So we just talked about the economizer wheel,
Yeah.
and so you said wheel stop. I'm looking at the code right now, and it says that it is you can use speed control on the wheel. It doesn't actually say modulating. So would you interpret that as saying that you can just stop the wheel, or you have to modulate it?
So we offer a VFD for modulating wheel on all of our wheels. So if you do want to have that, you could get it. The advantage with a modulating wheel, let's say it's pretty cold outside, but there's a request to have cooling in the space. Well, instead of stopping the wheel, you could slow it down a little bit, and you could basically slow it down to the point where the leaving air temperature is like 55 going into the space. And so that's how it would work. So by having the modulating wheel, you're expanding the conditions on which you can do economizer mode because you have more options. You can slow the wheel down so that you could get that cooling if it was kind of cool outside. Whereas if you had stopped the wheel and it was 35 degrees outside, you would have too much cooling. And if you have the wheel spinning, it may not be enough cooling. So you're avoiding either running cooling or heating in that case to get that 55 on a cool day.
Wait for some more questions. You breezed through that, Bill. Good work.
Oh, thank you. Oh, we had three good questions there, so I appreciate those. But I'd take any others out there.
A couple more minutes. Yeah, here in Washington, I was just gonna ask that, Mark. Can it meet the high performance DOAS requirements? I don't know if you're familiar, Bill, but the high performance DOAS is pretty much energy recovery that can meet 80% sensible under 0.77 watts per CFM and have an economizer on it. If it's over 500 CFM, I've selected units where it does meet that criteria with the
Yep.
RVE and several of the cabinets with that wheel, with that polymer wheel. So I can answer that for you, Mark.
Just like everything else, it depends, right? It depends on the exact performance point. It depends on the cabinet. So it's hard to say yes or no, but we definitely have some applications where we can meet that requirement.
Yeah, there's a couple other spots in the country that have similar things, and yeah, if you're below, let's say, kind of a rule of thumb, somewhere around that 6,000 CFM mark, you can almost always hit that 80%. Another question for A2L in the interconnected space line. Dash rate 15, and you're good. I guess I don't quite follow.
That is a good question, David. We may look into that. We're noticing different regions of the country are addressing this differently. You know, some with separate sensors, if that's what you're referring to, separate refrigeration sensors. But I may reach out to you on specifics about that. That's a really good question. Honestly, it's a question we've been talking about internally at Dorsey because we're hearing different things from different designers and different engineers regarding that. So I don't think we have a perfect answer for you there.
Thank you, Chris. Usually I try to put a few more jokes in my presentation, but I didn't have too many today, so.
That's all right, Bill.
It's hard to make jokes about air source heat pumps.
I will say,
go ahead, Blake.
real quick, Chris, I did just select a DOAS that met that high performance DOAS requirement. It was with the RVE 20 cabinet, which is the smallest cabinet available. And I think it was at 900 CFM, 0.75 inch static. And it was able to go all the way down to 500 CFM to meet that criteria. It was electric heat, no cooling, with an energy wheel. So that was a recent project. So that was cool that it was able to hit those points.
And like I mentioned in the presentation there, maybe if you did have cooling, you might have to jump up to cabinet size, but you should still be able to meet it.
Mm-hmm. Chris, were you gonna say something?
Yeah, I would say we also have plenty of other, energy recovery only products, right? With either just the wheel or just the core. If any of that supplemental heating or cooling is not needed. So keep that in mind. And, if you'd like to see one of these units in person, we always do our factory trips up to Schofield. So if that's something you're interested in, please let us know.
We'd love to have you.
With that, I think, yeah, the weather's getting good. I was up there a couple weeks ago. It was getting a little bit better still. But yeah, we'd love to take you, or if you want us to do more webinars or presentations, reach out to your Dorsey rep. And with that, I think we'll wrap it up here. Next week we got fabric duct. So hope you guys can join us then. We're talking about principles of fabric duct, their applications and product options. But if you have any more follow-ups, reach out to me, Chris, or Scott. Bill, thank you so much for presenting, and we hope to see you guys next week.